Hello everyone. Today we are going to be going over the four quantum numbers n, l, m sub l, and m sub s. And we're going to be talking about the shapes of the orbitals, which can be determined by the L quantum number. And we're also going to go over some practice questions. Starting off, we have the s orbital, which is a spherical shape, always. The p orbital is usually like a bow tie, either oriented in the vertical or horizontal. The d orbital is a little bit more complicated. It's like a clover, or it could also have this weird shape here, which can be described as a donut or a ring. And then the f orbital is too complex to draw. So now let's say we have four different values of n, 1, 2, 3, and 4. For each value of n, there's a different amount of allowed subshells. So when n equals 1, we have one allowed subshell, which is 1s. When n equals 2, we have two allowed states, 2s or 2p. When n equals 3, we have three allowed states, 3s, 3p, or 3d. And when n equals 4, we have 4s, 4p, 4d, or 4f. And now when we're talking about L, which is the angular momentum, whenever the subshell is s, L equals 0. Whenever the subshell is p, L equals 1. Whenever it is a d subshell, L is equal to 2. And for the f subshell, L is equal to 3. Now, m sub L is the magnetic quantum number, or it defines the orientation of the shape. So, remember when L was equal to 0, that was the s orbital. When L is equal to 1, that's the p orbital. So here, m sub L can help determine which variation of shape we will get. So in order to determine m sub L, we know that it is plus or minus L. So it ranges from negative L to positive L. So let's say that we have a 4s subshell. We draw a line knowing that it only has two allowed electrons in its subshell. So that means that m sub L can only be 0, because in this case, L is equal to 0. Now let's try something a little bit more tricky. Let's say we have a 4d subshell. So we draw out the 5 lines representing the amount of electrons that the 4d orbital can hold. So because we know that it's a 4d subshell, we know that L must be equal to 2, using the chart that we had earlier. So that means m sub L can be from negative 2 to 2. So that means that this orbital over here would be negative 2, negative 1, 0, 1, or 2. And we're going to go over questions that involve asking which subshell would the highest energy electron be in. So just as an example, let's say we had 4d4. It would be which value of m sub L would have the highest energy electron. So we fill this, not violating Aufbau's principle or Hund's rule. So we see that the electron fills the one orbital there. So that means m sub L is equal to 1 would be the highest energy state. Now moving on to the last quantum number, which is m sub s, which is the spin. Now m sub s can either equal positive 1/2 or negative 1/2. So let's again say we have that for D subshell. So we're going to draw out our 5 lines for the D subshell. And now let's say there's 4 electrons. So we're going to start filling this up. Notice this is pointing up. This means that there's a positive 1/2 m sub s. Now let's change the number to 8 again. 6, 7, 8. Now because this one's facing down, m sub s would equal negative 1/2. So now we are going to do some practice on these orbitals to try and find the quantum numbers of the specified electron. So starting with the 2s subshell, we know s's can only have one subshell, so we draw one line, and there's one electron designated up here. So we draw one arrow up. From this we can get all of our information about our 4 quantum numbers. N is equal to 2, L is equal to 0 because it is the s orbital, therefore m sub L also has to be 0, and the spin is positive 1/2. Moving on to the 3p6 orbital, we know it goes SPDF, so P has 3 lines. 1, 2, 3. And it has 6 electrons. We want to find what that 6th electron is. So we fill this in order. And there it is. N is equal to 3. L is equal to 1. M sub L is equal to 1. And just as a reminder what m sub L is, if it were this one over here, that would be negative 1 m sub L. This would be 0. That'd be 1. This means the orbital is 1. And the spin is negative 1/2. And for the d orbital, we have to draw 5 lines. And there is 7 electrons. And there it is right there. So now we can get all of our information. N is equal to 3. L is equal to 2. S, P, and D, so therefore D is 2. M sub L is equal to negative 1. I'll write these numbers in orange above here for M sub L. And the spin would also be negative 1/2. And that's how you find the quantum numbers of a specified electron in any given subshell. Now we're going to do the exact same thing we just did, except in reverse order. So let's say we have N equal to 3, L is equal to 1, M sub L is equal to 0, and M sub S is equal to 1/2. So we know that N is equal to 3, so we know that the subshell starts with a 3. We know L is 1, S is 0, and P is 1, so it's a 3p orbital. So we're going to draw out our 3 lines for the p orbital. We know M sub L is 0, so that would be in this one right here. And this would be plus 1, minus 1, just as a reminder. That means it has to be in this orbital right here. But because we know the spin is positive 1/2, that means that it has to be the 2nd electron. If we were to continue to fill this, the 5th electron has a negative spin, but we want that positive spin. So therefore, your answer would be 3p2. We're now going to do some practice with some orbital diagrams, and using some elements from the periodic table we're going to draw out the complete orbital diagrams. So starting off with an example, let's use oxygen, which using the periodic table we know it has 8 electrons. Now let's say we want to draw the orbital diagram for this. So in order to get the correct order of the subshells and to fill them correctly, we have to use the chart that we drew earlier, and we can draw arrows down to determine the order of them. And you can just draw the 5 subshells below as well. So referring back to the earlier parts in the video, we know the S subshells have 2, the P's have 6, D's can have 10 electrons, and F's can have 14, but we will not be needing the F subshells in this case. So what we want to do is we want to fill going down like this in the order the arrows hit the subshells. So you don't need to memorize it, you just need to memorize how to write this down. So using this information, we know there'd be 1s, 2, so that's 2 electrons down. The next one would be the 2s subshell, completely filled. Now we have to go up to the third arrow, which is right here, follow it down, and then we get the 2p, 6, but it's not 6, it's actually 4, because we want to make sure that we get 8 electrons. So to verify our work, we're going to add these up. We get 8 electrons. So this is the complete orbital diagram for oxygen. And we're going to do another final example using the element of phosphorus, which has 15 electrons. So we're going to do the exact same thing we did before. We start with the 1s, or subshell completely filled. The 2s subshell also completely filled. This time the p orbital will be completely filled. Moving down to 3s, that will also be filled. And now we have to start at the 4th arrow over here, move down. So we're at 2 plus 2 is 4 plus 6 is 10 plus 2 is 12. We're at 12 so far, we need 3 more. So then we'll get 3p, 3. And there's our complete structure. One more example. Let us do, let's do potassium. That is 19 electrons. So we're going to do the exact same thing above, writing these all out in order, but that's at 15, so we can fill it up to 18. But then we need to get one more from the s orbital. And of course you can do this for any element on the periodic table. You will just have to start to use the f orbitals later on once you get down to the 4th row of elements. Thank you for watching today's video, and stay tuned for a part 2 explaining more about orbital diagrams and quantum numbers.